This is in chapter 2, section 2 at the very end, beginning into section 3. We're looking at vectors in a moment, and we're looking at position time graphs. I want to talk a little bit about yesterday, about wrapping up this piece about the air resistance challenge. About a week ago, we talked about what you learned. We went through some different pieces. What I'm curious is, based on our results we had yesterday, are there insights that you have? Like, what did you see? What was let's talk about the fastest pieces. What did you see about the fastest little something? Smaller. So certainly the ones that seemed to go faster were the ones that were smaller packages, right? Okay. What else? Please. Okay, there was more density. In other words, remember, density is mass divided by volume, right? So we're putting all of that mass in one smaller area, which is excellent. Does that mean that if it's more dense, if it's more heavy, it falls faster? No, I hope we've dispelled that myth for you. That no, it doesn't matter about how much weight you have, how much mass you have, it'll still fall at that same 9.80 meters per second squared. Sir?
The one that fell the fastest had like smooth, rounded edges.
Nice. So there was some rounding to it that allowed that air to flow over it, right? Which is very good. I like that thought. And again, you all had a lot of different designs you were choosing. I like them. I liked the variety of stuff that we had. It was very cool to watch and to see. It would have been funner if we could have had maybe a double elimination or triple elimination to see. Would have gotten a little more complex than we were looking to do with the time frame. But it would have been interesting to see if that little piece would have won out, even if we did it multiple times. Anything else that you learned? Please. Okay, the air will certainly play with it differently as it falls, that resistance, right? Because we've got the force of gravity pulling us down and the air resistance pushing us up. And how are we minimizing that for the fast one? How are we maximizing it for the slow one, right? Let's talk about the slow design. What did you notice about that? It was very interesting, the design that won. Okay, so it let the paper kind of flow and move to catch those currents rather than being directed like an airplane or something like that. Though we had the one glider that I thought worked very nicely. They very quickly moved it into this flat plane and then moved down. That was very solid. And there was a number of you trying to get that, turning it from a straight down motion into some sort of forward motion, which I liked. What else? Yes? Yeah, very flat, right? Not rounded, spread out. Yeah, it was excellent. It was excellent. Somebody had taken a paper and chopped it all into these small little, like a chain almost. That was you? Oh, and it didn't work that well? I was just curious.
It felt faster than the other.
Oh, it did? Okay. I was just curious to see. I was thinking about something like this. This would have been a pain in the butt if he would have chosen to make this his actual thing. I'm not sure it would have been tall enough to hold it up above the rail. But I was curious how that would work. Because, man, it's just got everything all spread out, this big, long chain. But what's the problem with this? Why do you think? Because he says this did not fall as fast as some of his other designs. What would be the problem with this? Sure, different angles, so you're not going to get it all pushing, in that upward direction. It's very long, so that was a difficulty. Right. Yeah, there's really not a nice flat surface for it to grab onto, right? If we could have somehow put some material between here, now we'd be talking, right? You'd have a nice big, almost a sail parachute going down. The same way, Matt, I know you did a bunch of those. Very similar to that parachute kind of thought, which I like. It was good. We did all of this to get you thinking in a couple of ways. Number one, thinking like an engineer, right? Having a problem, coming up with designs, testing prototypes, making redesigns, and then actually testing in the real world how your design worked. It's very much that engineering process we go through. And we did this as an introduction to acceleration, velocity, position. So that's what we're talking about here on page 40. I wanted to give you this kind of a quick peek at these vectors, which was something we talked a little bit about in our last unit, but I wanted you to make sure you saw this piece. This is showing you what vectors are, right? These arrows. And the key is that the arrow length means something, right? So they're saying that this is 5 kilometers east and 2 kilometers east. You add them together, you get a resultant that is 2 plus 5, 7 kilometers. It's crazy, the math, right? Okay. But you see that there's a proportionality to it. If you were to take this and put it here, double that would be just a little bit less than the 5. They should be proportional. Does that make sense? As I've met with some of you to talk about the retakes for your assessment, which today is the last day to do that, right? It's on Schoology that today, I think, is the last day for us to talk about a retake. I'm not going to take out a ruler and measure your vectors in the future, but I do want them to be, they should look proportional. Does that make sense? All right. And the direction does play a role. See how these guys are going to the right. So again, if you think of your little north, south, east, west, right? Since it's moving to the, that's a west, not an N. Since it's moving to the right, we assume that's east. Does that make sense? Down here, this 2 kilometer one is moving to the left, right? So we've got 4 kilometers this way, east, 6 kilometers west. So the resultant, when you add those together, means you went a total of 2 kilometers west. This makes sense? Please.
You showed us that video of the guy in Ohio in the NASA tank.
Okay, yes.
Yeah. And they made that chamber and they took out all the gravity.
All the air.
All the air.
Mm-hmm.
They dropped at the same time. But with gravity though, isn't it going to affect like if it's a more dense object, a feather, the thing's still going to be heavier with gravity?
Sure. So you're thinking about the density. So in other words, the feather has got all of these little wings to it, right, that kind of catch the air as it falls, right? And that's what slows it down. Very much like what you guys were trying to do with your paper, right? If I remove all of the air molecules out of it, now there's nothing for those feather wings to grab onto. So therefore, no. The gravity pulls both of them down at exactly the same time.
So it is the air resistance.
It's the air resistance that slows the feather normally. You're correct.
Gravity's the same.
The gravity is exactly the same.
And then no effect.
No change as far as between the amounts of mass. Because not only does the feather have the wing pieces, right, that hold it up, it also has much less mass. So that's why you all think, oh, well, it has to fall slower. It's because of the air resistance. Yep. It's a key point. Thank you.
What was that thing you were talking about with the Galileo?
Right. He did this kind of same experiment. He was the first one, or at least our famous one we talk about, on the Leaning Tower of Pisa in Italy, where he had 2 stones very similar size, but different weights, right? So different densities. Same volume, but different masses. Simultaneously, and they hit the ground at the same time. And everybody's like, wait, what? So again, he tried to get rid of that air resistance variable by making them about the same volume. Does that make sense? Their mass was different. If you held them, you could say, oh, no, this is definitely heavier than that one. But by getting rid of that air resistance piece and just dropping them, they hit the ground basically the same time. Sir? So weight, and we'll learn more about this, but weight is simply gravity pulling on mass. So when we step onto a scale, right, we're getting weight. We're getting our planet's gravity pushing us down onto that scale. My mass is something that's different than that. My mass is just the amount of material that's in me. So let's say I weigh 200 pounds here on Earth. I go to the moon that has a fifth of the gravity. I step on the same scale, I only weigh 40 pounds now. Oh, I lost 160 pounds on the moon diet. Nah. A lot higher. You've seen pictures of these astronauts walking on the moon. I say walking in quotes. They basically bounced like kangaroos because it was just more efficient. It was easier than just walking. And they would just kind of leap, and the gravity would slowly bring them back down. They bounce again. Yeah, it would be very cool. Yeah.
Thinking of the fact that you would die if you were in that chamber with all the air sucked out.
Right.
What would it be like? Would you be a lot lighter? Would you?
No, because the gravity is still the same. There just wouldn't be the resistance. Yeah, for you and I, we don't really deal much with air resistance on a day-to-day basis. The only time I really think of would be like when we stick our hands out of the car window and you can feel the air pushing against you. No, it really wouldn't. Yeah.
Would there be no pressure in that room as well, since it's brought out all the air?
Sure, right, because the pressure, what we talk about as atmospheric pressure is just the air pushing down on top of us, yeah.
Because there's no air.
And that's why they have to build the walls of that so strong, because the air from the outside is trying to collapse that chamber. There's no air inside of it to push against it, so they has to build that really, really strong, those walls. We good? This is good. I wasn't planning on going that direction, but I don't mind at all. It's excellent. Okay, so let's move to here in section 3 of chapter 2. We have some position time graphs. Let's look at, on the top of page 42, and again, I apologize, I don't know why I didn't take a picture of this one and put it up here for you. The question for example problem number 1, when did the runner whose motion is described in figure 11 reach 12 meters beyond the starting point? So can you answer that question for me? 12 meters beyond the starting point. When did she get there? Well, I'm on page 42. It's not the one that's on the board. It's on page 42 here. Example problem number 1. About 2.5 seconds? How did you figure that out?
Because you have the 10, and you also have 15, and then you also have a dotted line that looks to be about 12.
Sure. So again, you go to 12 meters on the y-axis, right? You slide over to the line, and then you come down to the x-axis, and sure enough, there you go. It's about 2.5 or 2.4, they call it, seconds. This is kind of duh, right? This is pretty straightforward. All right, I'm just making sure you're with me. How about where was she after 4.5 seconds? 22, 23 meters. Okay. So let's look at these position time graphs that are up here on the board. In figure 12 there, how would you describe this motion? Right? So position on the y, time on the x. Somebody want to describe to me what's happening here? Got one? That's it. Hang on. I want to see. Give you time to think about it. I have 1, 2 hands. 2 folk willing to describe what's happening here. All right, Brendan, what do you think?
As time goes on, his speed is slower.
Okay. So he's saying as time goes on, his speed gets slower.
Or he loses.
Because this is a position time graph, right? It's not a velocity time graph. So we're saying his...
Back as time goes on.
Okay. So he was 125 meters away from me. I'm standing here at the origin at 0. And he started driving toward me. And it took him 5 seconds to reach the origin. Are y'all with me? But then did he stop? He just kept going right on past me, right? And so he kept going again, and you could keep that graph going, how far he went. Did anything change with his speed? How do you know? Give me a hand, because I want to hear this one. How do you know, Lauren? Are you comfortable the slope of that line is absolutely the same the whole way through? Right? And slope is rise over run, position over time, meters over seconds. That's velocity, right? Meters per second is speed, is velocity. I'm sorry? How do you know? Can anybody answer that question? How do we know that he went past the starting point? Yes, ma'am. Perfect. Here's our 0 point, right? And the line actually crosses over that and keeps going. It's well done. Yes? Okay. All right, let's look at this one here in figure 13. In figure 13, can somebody describe for me what's happening? And again, position time. Lots of different kind of graphs we can use. This is a position time graph. Can anybody describe what's going on here? Okay, let's do this then. I'm going to pause. In your groups, I want you to talk about it. You're all afraid to talk to me. On your table groups, tell me what's happening. How would you describe the motion here in figure 13? Go for it. All right, who wants to share with me what's happening with these in figure 14 here, or 13? Thank you, Nels. Ah, how do you know they're going the same speed? Their slopes are equal, the lines are parallel. Perfect. And you said something about their starting positions? What about it?
Object B starts farther ahead than object A because it's higher up on the y-axis.
Excellent. So if there's some sort of starting point, and again, in the problem that accompanies this, it says that upward is east. So this guy in B starts a little further east, a little further down the road, right? And the guy behind him starts actually a little behind the origin, a little bit west. But they're both walking east. How do I know that? I think it's your question, I promise, in a second. How do I know that they're both going east? They're both going in the positive direction, right? The slope is positive. If they were negative, they'd be walking west. And again, that's simply because we defined upward as being east. We cool? Your question, Gracie. Mm-hmm.
Does that mean there's increasing or
It's good. If this was a velocity time graph, you'd be correct. That there's, because the angle was going upward, their speed was increasing. But because this is a position time graph, we're simply saying that their position is getting more positive. The speed would just be the slope of the line. Because speed is meters per second. Meters divided by seconds. Slope is rise over run. So for a position time graph, velocity is the slope. That's a nice test question, by the way. For a position time graph, the slope of the line is velocity. All right? Making sense? Let's go to the next one. This one is over on page 44. It's example problem number 2. All right. In your groups, would you please discuss what's happening in this graph? In your groups. Go for it. All right, let's jump back in here, friends. Somebody want to describe what's happening here? I've got 1. I've got 2, 3, got 4. Okay, I got a few of you guys. All right, tell me, Ryan, what's going on?
B starts 50 meters behind A. B is moving faster, so they meet up at 45 seconds.
Nice. So it's a race. It's actually a pretty nice head start. 50 meters. Man, that's that's a long head start, right? And you said that B's going faster. How do you know that?
It covers more meters in less time.
Okay, in less time it covers more meters, right? Is there any other way that we can know that B is faster? Sir? The slope is higher, right? A steeper slope in that positive direction. Cool. The question that the example problem asked was so in other words, at what distance do they meet up? And based on the graph, what would you say? 190, Yeah, I think they came up with 180 something, if I remember correctly. But yeah, around a 190. It's tough. We can't tell exactly from there. But yeah. Yeah, about 190 from the origin. How long? Like, how long had the race been going when they met up? Cool. About 45 seconds there. And they were pretty close to the same area for a while because their velocities weren't hugely different. It wasn't like, one guy was strolling along, the other guy was sprinting. They were both running at a decent speed. A little faster. I would agree. 50 meters head start. Man, that's a good head start. Are you with me, friends? And again, what kind of graphs are these? Position time. Okay? All right, check out this next one is over in the practice problems there on 2.3 on page 45. This has got a little different information. What is this telling us? Oh, okay. Oh, so the units changed, right? We've been doing meters per second. This is kilometers per hour. Okay? So we assume they must be driving or riding a bike or something like that. Probably not running or walking. Though 1 kilometer is not very far to go. So they could be walking. What's different about this graph than the other ones? It does have a grid. Okay, we talked about the units already. Good, that's good. We talked about the units. Now they're both going the same direction. We know that because why? Both the same slopes, right? If they were going opposite directions, they'd have opposite slopes. Both lines are angled going upward, right? Sure. But again, that is not necessarily giving you information about distance. Remember, the slope is talking about velocity. So because the lines get further apart doesn't necessarily mean the people are getting further apart. Because actually, once they get up here, they've both reached 6 kilometers away from the origin. So once they get here, they're actually in the same position. Okay, this Juanita went faster, certainly, right? And you know that because it took her less time to get to 6 kilometers, right? Sir? That's the key I wanted you all to see. Heather started later, right? 1/10 of an hour, so she started 6 minutes after Juanita did. Okay, so instead of giving a distance head start, here they showed it as she gave her a time head start before she went. Does that make sense? Yeah, Juanita, and then she was just kind of sitting there waiting for her to come, right? Because she got here at 1.2 hours, and she got here at 2.1. So, I mean, she was sitting there almost an hour waiting for her. Man, had time to catch a burger, enjoy, relax. Are you with me, friends? Do I have one more? I thought I did. All right, one more. This is on the bottom. Oh, where is this? This is on page 48, example problem number 3. This is where we're actually looking about how we calculate velocity. So what's our equation for velocity? Sure, distance over time. Did you guys ever, yeah. Oh, there was a name. What's the name of that old equation? Distance is rate times time. Dirt. The dirt equation. Did you all ever hear that called that? No. Okay, never mind. You did? Thank you. Whew. Somebody help me. I called it the divot equation because distance is velocity times time. Right? So we're just switching it around to find for velocity. Now, in your textbook, they use a little different letters, right? They say the velocity equals delta x over delta t. So let's do some reminders. What does delta mean? The change. Yeah. So delta means final minus initial. So delta x is x final minus x initial. Why did they use x? And it's not just simply because it's unknown. There's actually a reason behind it. It's not like just algebra where they picked x. No, you're right. You're right. But what direction is this motion happening in? What plane? It's in the x-axis.
So then why not delta y?
So they have delta y when we talk about free fall. It'll be delta y. Are y'all with me? Because it's an x-axis, they call x as distance. And then time is just simply, the delta t is just change in time equals tf minus ti. Pardon me. Okay, sorry about that. Normally your TI is going to be what? What do most folks start with when we try and measure time? We start at 0, right? 99.999% of the time, you start at 0. So basically this is just T. So let's look at our graph here. How fast is this person going? Okay, so we take a spot where it crosses, right? So 12 meters in 7 seconds. Can we do that math? Just dividing, right? Why do I take when it crosses? Can anybody answer that? Because it's a good question. Say again? Right. It's simply about getting nice, easy to deal with whole numbers. If you actually graphed it on a calculator or on your computer, you could take any point on that line, and you'd still get the same velocity. But it's just easier for us to calculate that way. Yes. And so therefore 1.7 is the average velocity. So they'll call it this. That little line over top of the V, that just means this is average. This is over that whole 7 seconds, she's going an average of 1.7 meters per second. There's another kind of velocity called instantaneous velocity. It's how fast are you going at this particular moment. We'll talk a little more about that. Most of the time we deal in averages, because it's a pain in the butt to get instantaneous velocity all the time. Have I thoroughly bored you? Hopefully not too bad. All right. We did all of this to prep you, to prepare you for, one more equation. For one more equation, which is here on page 50, the very end of section 2.4. That if we're trying to find the distance somebody traveled, we have to take the average velocity times its time, multiplied by time. So this is our DIRT equation, right? Or the Divot equation. The distance is rate times time. Or distance is velocity times time. But we have to also add to it, what does it say there? XI. In other words, did you give them a head start? Were they already someplace in front of the origin before they started moving? You just simply add that distance here. So if I'm racing Matthew and I gave him a 10-meter head start, and I want to know how far did he travel over the 10 minutes we're racing at a certain velocity, you have to add your head start here. It would just be 0. That's fine. You would just ignore it. I would just ignore it. Yeah. Because again, often our xi is 0. Often. But not always. X is distance in the x dimension, in the x plane. V is velocity, T is time. Mhm. Initial. So it means the starting X. Did you give someone a head start, or were they staying where they were? Okay. Whew. It's well done. What I want you to do, please, is I want you to read for tomorrow, page 60. Yeah, let's do those two sections. There's a lot of problems and stuff. So from page 60 to page 74. So it's 3.1 and 3.2. Thank you very much. Have a lovely rest of the day.